Okay, so welcome back. This is our third session of today. Let me again share my screen. So we want to understand the recursive approach, all right? So recursive approach basically exploits certain properties of the value function and the Bellman equation, all right? Before I go any further, let me remind you of one thing. So here, we didn't prove, okay, so let me once again write the Bellman equation. So we didn't actually prove, oops, what's going on? So if this is a legitimate optimization problem, okay, with constraints expressed in this way, okay, and K0 given, all right? We have not really proved that a solution to this problem is identical to the solution of our original problem. Okay, so we haven't proved that, okay, and we are not going to do that, but it is under certain conditions. So you can look at Stokey-Lucas, okay, you can look at Acemoğlu, and there are other references as well, okay, but we are not going to do that. I mean, we are not going to spend so much time on this. We just want to say, of course, something specific about these functions. So in general, what I said before, so U continuous, F continuous, concave, twice continuously differentiable, all right? So these are still important. Of course, if there is strict concavity, then this guarantees the uniqueness of the optimal path. Then there is this boundedness assumption, okay? I will spend some time later on about boundary and bounded and unbounded functions. For now, I mean, don't mind whether your utility is bounded or not. In most cases, utility functions are not bounded, but we still have ways to characterize solutions. Okay. So why do we need such conditions? And of course, I also should write beta is between 0 and 1 always. So that's very, very important. Okay. So why do we need such assumptions? Because we want to have V, okay, to have certain properties, and we want this set, so the feasible set, so this is usually in the general form, it is the correspondence. So we want this to be to have, again, certain properties such as compactness and convexity, etc. All right, and continuity. So continuity is a little bit different for correspondences. So there's something called upper continuity, upper hemi-continuity and lower hemi-continuity, and other things. I don't want to go that detail. All right. Again, I want to deliver this lecture in this hour and in the next 2 weeks in a pragmatic point of view. So I want you to show you a couple of methods, but for V, we want this to be generally continuous and differentiable, concave, and most importantly, unique. Okay, so the idea is that we want to. So this is. So this equation will be written as a mapping. All right. once we write this as a mapping, we want to ensure that it is a contraction mapping. Okay, in a contraction mapping, of course, let's say this is a mapping T, okay, an operator, and this is some function. So so given f, that gives you something else, right? So T is a mapping in the space of functions. Let's denote them in this way, for instance. This is a space of functions, okay? So T is a mapping, so it takes a function f and gives you another function in the same space, okay? So we want this mapping to be contraction mapping. So for contraction mapping, there are a couple of properties. Perhaps next week I can talk about these. But one thing is that one, all right? So beta is less than 1 is important for T to be contraction. So when we express value function, so the Bellman equation as a contraction, as a mapping, then we would need such thing. And there is also this monotonicity condition, monotonicity condition. Maybe we can look at some details of this, but in general, you don't have to deal with all these topological stuff. Okay. So where are we? We are at the problem of solving this problem. Okay. So I will give you the general optimality results. And you're going to understand that these are pretty similar to ones we obtained for the sequence problem, all right? So once again, non-negativity. And now I want to write this as simply as an equality because I know that U is increasing, so I always use all the resources, okay? Now, one thing we want to do is to choose CT optimally, right? So how do you choose CT optimally? Well, obviously you want to have U prime CT. So you want to have CT to maximize the right-hand side, right? Because this whole thing is what you try to maximize, okay? So you want this CT, the choosing CT, the CT you choose to maximize this part. So there must be some sort of a first order condition, all right? So you have U prime CT plus beta, then you have, if of course now, you see what do we require here? We want this to be differentiable, right? Now, because I am differentiating V with respect to KT plus 1, and I am differentiating KT plus 1 with respect to CT. And this must be equal to 0 if CT is positive. Okay. In general, of course, there is a non-negativity constraint. So you have to write the full set, right? You have to write less than or equal to 0, then CT times this is equal to 0, then CT is greater than 0. But here I'm taking a shortcut. Okay. So for your control variable, you need something like this. Okay, for your control variable, you want this to be true because your CT must maximize the right-hand side. All right. Now there is also this thing called envelope condition. Okay. Now envelope condition is sometimes called Benveniste-Shainkman formula. So these are the economists or mathematicians. Benveniste-Shainkman formula, okay? So the idea is this. If the policy function we're going to choose at the end, CK, if that really maximizes my utility, my intertemporal utility function, then this must be the value function I must have at the end. Then this must be true, right? By the envelope theorem. I'm taking the derivative of both sides with respect to KT. So KT plus 1, how do I write that? KT plus 1's derivative, so KT plus 1 is equal to FKT CKT, right? So, okay, let me first write explicitly. So this must be the case, right? Because if KT changes, the effect of this change on the left-hand side must be equal to its effect that you will find on the right-hand side. And this further satisfies this. So F prime KT minus CT KT, right? Now, if you look at this equation carefully, let me use green here. If you look at this equation carefully, you realize that because of this one, we have V prime KT equals beta V prime KT plus 1 times F prime KT. Okay? You see why? Look at this. So this one and this multiplied by this one is equal to 0, right? By this equation. Okay, because KT, so this is equal to minus 1. This one is equal to minus 1. Okay? So then, to summarize, what do we have? We have for the simple problem at hand, we have, first, a first order condition with respect to CT. It is equal to that. Okay. Then we have the envelope condition, which is equal to that. And then, of course, we have the transversality condition as well, right? Remember the transversality condition? It was beta T, U prime CT, KT equals 0. Okay, so that last part is usually not imposed, but it is already there. So if you want to do perfectly, if you want to create the full solution in a numerical manner, we have to check whether that's true. And usually in economic problems, in such problems, we allow the consumer to jump to the saddle path in the initial point. So it's always satisfied. All right. Now, let me use another color here. So now I have U prime CT equals beta V prime KT plus 1. V prime KT equals beta V prime KT plus 1 F prime KT. Okay, I'm gonna do a better way, I guess. So V prime KT equals beta V prime KT plus 1 F prime KT. Okay, and we have the other stuff. Now realize that if I denote V prime KT by, let's say, eta t or QT, I mean, let's use Q. Okay, it doesn't really matter. Now V prime KT plus 1 becomes what? QT plus 1, right? So what do you have? You have QT equals beta QT plus 1 F prime KT. You see? Now timing is of course different because now, be careful, I mean, don't confuse this with the original formulation. Now you have U prime CT equals beta QT, right? Sorry, beta QT plus 1. So U prime CT plus 1, if you want to write the earlier equation, it must be beta QT plus 2, right? So you have to be dealing with QT plus 1 and QT plus 2. So you have to iterate this. If you iterate that, you have QT plus 1 equals beta QT plus 2 F prime KT plus 1, right? So you have at the end U prime CT divided by beta divided by U prime CT plus 1 divided by beta, okay, equals beta F prime KT plus 1. Then that's the same earlier equation if you look at this carefully. Okay. So once again, even without knowing V function, we can arrive at the same dynamical system with the same initial and terminal conditions. So that part works. Okay. What we will do is this. So there will be first the method that is typically called guess and verify. This is the method of undetermined coefficients, actually. First, I will show you this. Next, I will show you value function iteration. Then I will show you policy function iteration. Then we're going to talk about perturbation methods. Now, in terms of tasks, this is basically algebra. These are projection methods. So you basically compute stuff, okay? And here you kind of approximate the results using perturbations around the steady state. So if there's a steady state, you're gonna perturb the system in such ways, okay, so you can characterize the solution, okay? There could be linear approximation, quadratic, or even higher order, okay? So the order could be even larger, all right? I will show you. I will talk about this. Not spend so much time on this, but I will show you how you can do it in computer as well. Okay. So let's start with guess and verify. It's very simple. It is not suitable for all problems that you're gonna face, but it is intuitive. All right. So let's try to understand it. So our problem now, let me write it in a very specific way, with utility being natural logarithm and production being Cobb-Douglas or power function. So then we have the Bellman equation. And then C plus, why does this go away? Okay. Beta V. So here I have lambda positive, alpha between 0 and 1. So I have V KT plus 1. So this is CT, this is KT. I'm not writing the other stuff, but it's there, as you know. Now we're gonna guess. Step 1. Guess VKT, right? Because I told you that if I know VKT, that solves many of our problems. Okay? So let's write a guess, such as VKT equals phi plus theta times ln KT. Now here, these phi and theta are coefficients that are now unknown. They are undetermined. So this method is called the method of undetermined coefficients. At the end, we want to confirm, okay, whether these are actually real numbers and fixed and satisfy this VKT. All right. Now, how did I choose the logarithmic form? Well, the simple reason is that I know that this is true. Okay. But if you look at your utility function, okay, and if you look at your production function, well, you realize that if savings are constant, think simply, I mean, think heuristically, all right? If I spend a constant fraction of my income to saving and the remaining fraction to consumption, then if I put consumption there, then it will be a logarithmic function of capital stock, right? Because again, I have this production function, right? So now I don't know, but I have some sort of a way to guess, all right? Now, if that's true, step 2 is to write VKT plus 1, right? Because this is what I need. This is what I need, right? To solve the right-hand side. So VKT plus 1 will be simply this, right? ln KT plus 1. So it will be phi plus theta, the natural logarithm of, remember the constraint, FKT minus CT. All right? Now, what's your problem? Now, step 3, find CKT that maximizes the right-hand side of Bellman equation. Okay? Because now I can solve the problem. I know this, right? I know this. I already know that part. This is basically, I assume, knowing that part. So I'm gonna just find it. So if I do it, what do I find? I have 1 over CT, right? Plus beta theta minus 1 divided by lambda KT alpha minus CT, right? And this must be 0. So I have I have what? I have lambda kt alpha minus ct equals beta theta ct. So ct equals 1 over 1 plus beta theta times lambda kt alpha. Okay. Now, is that correct? I don't know. I don't know theta, right? I don't know this parameter. So this theta is not known. So I cannot really tell whether this is correct or not. But now I can check. Okay. So step 4. Step 4. Write the Bellman equation, right? So now I have phi plus theta ln kt on this side, okay? And I have natural logarithm of, what was that? What was ct equal to? 1 over 1 plus beta t, right? Lambda kt alpha. Okay, so that was that one. Plus, I have beta phi plus beta theta, right? If you carefully write it, ln kt plus 1. So kt plus 1 will be what? Kt plus 1 will be 1 minus the consumption marginal propensity to consume, right? So it will be 1 minus 1 over 1 plus beta theta times lambda kt alpha, right? So now what you are looking for is this. I have 3 minutes, so I'm gonna leave the rest to you. So you're gonna find constants here, okay, and some other constants here times ln kt, and here you have, so let's say this is constants 1, this is constants 2. You have phi theta ln kt here, right? So you're gonna equate phi to constants 1. You're gonna equate theta to constants 2. Okay, then out of these equations, you're gonna find phi and theta as functions of let's say z function is a function of alpha, beta, lambda. These are your parameters, and this will be a function of alpha, beta, lambda in general, of course. Okay. Then, if they are really constant, etc., if you match these terms, right, this means they have the same function, right? Then you can verify it. Now let me also give you another exercise. After you complete this, try this exercise. Try this function, not the logarithmic one, but linear one. Okay, try this and you see how it fails. Okay. So if you want to reconnect again today, just let me know very quickly, because we have less than a minute. If you have very urgent questions, otherwise I will see you next week. Anyone? Okay, as you see, this is pretty standard. The first and very simple method that we use, and that is usually not very helpful in many problems, but this is essential. Guess and verify is an essential method. Work on it, and I will see you next week, and I can answer your questions there. Okay?
Okay.
Okay, see you.
Bye-bye then.
Thank you. Bye-bye.